Hello students, welcome to TAA's Tutorial Center where we make complicated topics very simple to understand. So if you are under natural in the applied sciences and you want to become good, you want to become better, you want to start thinking outside the box, then do subscribe to this channel because we break down complicated topics to something which you're going to understand in just a short period of time. Fima Zwibo! Zwibo dude. In this tutorial, we'll talk about the DNA replication. We'll start by first of all explaining the historical perspective of the DNA. After that, we'll talk about what DNA replication is. We'll talk about the three models of how the DNA replicates itself, and we'll start explaining now how does the replication comes about and how does it hint. Okay, so make sure you watch until the end where I talk about the enzymes involved in DNA replication, and it will be more like a story that you're going to enjoy. I tell you, it's not going to be boring. Okay, so who discovered the DNA? The guy who discovered the DNA is known as Friedrich Miesche. Friedrich Miesche. Okay, so this is the guy who discovered the DNA. He actually used to call the DNA not as the DNA, he was calling it the nucleon. Now, he used to call it the nucleon because it was very predominant in the nucleus. Then from there, this was happening in 1869. In 1869, then after some years, some guys were still studying the DNA to find out more about the DNA. So these guys came in. Friedrich is not the one who discovered that the DNA is made up of the two strands. No, the guy who discovered that is known as James Watson, or just going to put Watson. James Watson and Francis Crick. These are the guy who discovered that the DNA is actually made up of double strands. And we know that the double strand, there is the template strand and the non-template strand. This was happening in 1953. Yes, it was happening in 1953. This is 1869. Okay, then from there, some people again continued studying the DNA, or the DNA is this and this. So came two guys again. I love these two. So this guy known as Mesosan and the friend known as Tao. The first name for Mesosan, Matthew, and for Tao is Franklin. These guys studied the DNA and came up with three models. They came up with three models on how the DNA replicates. So these three models, they're the one which are going to tell us how the DNA replicates, and it's actually very simple. So let's talk about the three models. The first one is semi-conservative replication. And there is also conservative replication and dispersive. Okay, so these are the three models, and I'm going to explain each one of these models because one should know the same conservative model, the conservative model in the dispersive model. So we'll start first of all by this one. This one was not true, this one was not true, but this one is true. Now why is it true? That's where we're going. As we are saying, the DNA is made up of two strands. Let's call the two strands this one and this one. Let's say this is the DNA that we have. This is our double strand that we have. And we want it to replicate, which means from these two strands, we want to form another two strands for it to be 4. So that we have 1, 2. It has replicated, and we have this 2 as the new DNA, which is replicated. Now, how does it work? So one should know that the parental strand, each of the parental strand act as the foundation of the new strand. It acts as the foundation of the new strand. Now let's talk about it. We're talking about dispersive. What is this dispersive model talks about? It states that this is where the two molecules produced contains the parental strand and the new strand interspaced along each other. What are we saying? Suppose this is the new strand that we're supposed to have. The two strands that we're supposed to have. Now, what will happen is one of the parental strand will be like this. The parental strand, the new strand, again the new strand, parental strand, new strand, parental strand will be like a combination of the strands. So this is going to be called now one DNA, and it's made up of two strands. That is, this one has your parental, then this one has the new strand forming. And which means another one is going to form, and actually it's going to be somehow the same. It's going to be the parental strand, and the new strand is going to be interspaced along the length of the parental strand. Now this is wrong. You can't have the DNA which looks like this. No, this is not the way it is. Now let's go to the conservative model. What does it state? This is where the two DNA molecules produced, one is made up of two parental strands, then the other is made up of completely new strands. That is, you have this as your DNA. Then, after it replicates, you're gonna have something like this. The parental strand will be just the same as it was, then you're going to have the new strands as this when it copies. Now actually this is also wrong, because the parental strand, nothing has happened to it. It's just the same way as it was, and it's not acting as the foundation of the new strand which is forming. So this is wrong as well. Let's go to the semi-conservative. Now semi, remember what it means when someone says semi. Semi means half. Okay, now look, this one states that each of the parental strand act as the foundation of the new strand. Each of the parental strand, which means this one, and I get it, is going to act as the foundation of the new strand, and the new strand is going to form there. And again, this one will act as the parental strand for the new strand which is going to be made. So it's going to be like this, semi. Okay, so this one is accepted, but these were denied. Those are the 3 models that Messerschmitt himself came up with. Now, you see how it's very interesting talking about the DNA. Anyway, now let's talk about how the DNA replicates. What is DNA replication? Let's just talk about it a little bit. Okay, so we know that when you're talking about the DNA replication, it's just the process by which the genetic information of the DNA copies itself. So you have the DNA, then it copies itself. That is DNA replication, and we have said it is what? Semi-conservative. The parental strand, each of the parental strand is going to act as the foundation of the new strand which is going to be made. Now, replication involves nucleotide, which are the building blocks of the nucleic acid. It involves what? Nucleotides. Do you remember when talking about the nucleotides? Made up of the phosphate group, the deoxyribose, and the nitrogenous bases. That's when you talked about the nitrogenous bases. Kinda interested in that, but not that much. Remember, we talked about the nitrogenous bases, and you say there is adenine, cytosine, and remember, adenine binds with what? Thymine. By how many hydrogen bonds? By 2. And cytosine binds with guanine. How many hydrogen bonds? By 3 hydrogen bonds. That's the way it is. Now, you should take note of one thing here. The DNA is always, I repeat, is always semi-conservative. You just know that it's going to be very simple for you to understand how it replicates. Now let's talk about how it replicates. It's going to be somehow like a story. It's not going to be boring. I want you to think of it as a story so that you understand even much better. Okay, let's talk about it. Then finally, let's talk about the DNA replication. So the DNA replication process is actually known as the mechanism of DNA replication. Now let's start. Suppose you have this as your DNA, and we can see that it's made up of 2 strands, known as the double helix. Now the DNA replication process, it actually begins at the origin of replication. This origin of replication is identified by this amazing protein which is known as the initiator protein. Initiator protein. Now suppose this is our initiator protein, and looking for where the origin of replication is. Actually, that origin of replication is a part of the DNA which composes of many adenine and thymine. Do you know why? Because they are going to be bound together by only 2 hydrogen bonds, and that is going to be easily broken compared to where there is a lot of cytosine and guanine. So some are going to be difficult because we know that cytosine and guanine, they are bound together by what? 3 hydrogen bonds. You've seen? Okay, so we're choosing the origin of replication to compose a lot of adenine and thymine because they are only bound together by 2 hydrogen bonds, hence it's going to be easy to break them. Okay, so suppose this guy then it says that okay, that's where the origin of replication is. I need to take now action. Then it goes there, boom, it start opening it up. Now when it's opening this thing up, it's failing to break the hydrogen bonds. Then there will be, people in Zambia, whenever you see a fight, you go to watch. So a lot of enzymes will come in. So these enzymes, each of the enzymes is going to have its own functions. It will have a specific function on the DNA replication. What this one is doing will be totally different from what this one will be doing. The initiator protein there is trying to open it up. Trying by all means to open it up. Then, as it is opening it up, we can see this Y-shaped structure. This is known as the replication fork. This is known as the replication fork. A Y-shaped structure is known as well replication fork. So what will happen is an enzyme will come, this one will come to just break the hydrogen bonds. Like hydrogen bonds. And that enzyme is known as the helicase. The helicase is the enzyme which breaks the hydrogen bonds. It will be breaking the hydrogen bonds and it will be moving toward the replication fork. So it will be like this. Now, so these two guys that you're seeing now with the knife, they are known as the helicase. Now, we can see that as this helicase, they continue to break the hydrogen bond and move toward the replication fork. This DNA will be coiling as much as it can, because the more you will be opening it up, the more it will be coiling. Now, we don't want this coiling to continue. We don't want this coiling to continue because it's going to stop the helicase from moving. Now, what is going to happen is another enzyme is going to come in. We don't want this coiling. We want to remove this coiling. Now, this enzyme which will come in is known as the topoisomerase. The topoisomerase. Now, this topoisomerase is the one which is going to reduce the strain in the stress on the DNA. Now, what does it do? It actually does this. It will be cutting and sealing. Will be cutting and sealing. So there it is. Let there be cutting and sealing. It will be removing the part which is called very much and seal. Again, it will continue doing that. Now, look at this. As these two guys, they are cutting the hydrogen bonds. It's a bond. These hydrogen bonds, they will try to get back together. The same way you try to get back with your ex, but it doesn't work. Now, it doesn't work because of some enzymes which will come in again. So this enzyme will come in and hold this strand in this strand that now you ain't going anywhere. These are the proteins we're talking about. These enzymes, they are known as what? They are known as what? They are known as SSBP enzymes. Now, why are they known as SSBP? That stands for single strand binding protein. Single strand binding protein. They will be holding on the single one of the strand. Okay, so what we are saying here is this. We already know that this guy, this one is known as the what? The helicase. Then this guy is known as topoisomerase. And this guy is known as single strand binding protein. What do they do? So these guys will be the one now which are going to prevent the reformation of hydrogen bonds. So your ex and yourself are not going to get back because of the single strand binding protein. So far so good. Now let's talk about the strands. When this is now open, now the new strands will come in. The new strands, the one which we were saying, or they will be built on let me say on top of the parental strand. Now those strands, the first one I'll talk about is the leading strand. It's actually very simple. Now the interesting one is the lagging strand. So let's dive into it. Okay, so this is the strand now. We can see the helicase, this guy, and it's just continue cutting, and the topoisomerase there is doing its job, and the single strand binding protein, yeah, they are doing their job. Now these things you're seeing here, more like the bricks, those are the nitrogenous bases. Now we need an enzyme which will come and start building now the new strand, because we already have our foundation. Now we want to form the new strand. Okay, so the way it is, I said we're going to talk about the leading strand and the lagging strand. When talking about the leading strand, it is the strand which is formed from fifth from fifth to third. It will be moving from 5 to 3 toward the replication fork. That is the leading strand. Now the lagging strand is going to be formed in the opposite direction, that is away from the replication fork. So look, the strand here, it will be the leading strand, then this side will be the lagging strand. Okay, now before I even start talking about these guys very much, you should know one thing here. The nucleotide bases which are formed by on the leading strand and the lagging strand, the DNA enzyme which works is just the same. It doesn't change that now on the lagging strand is going to be this DNA enzyme which is going to build the new strand. It's actually the same, and that is the DNA polymerase 3. DNA polymerase, some people say polymerase, some say polymerase. So pronounce it the way you can pronounce it. That is the DNA polymerase 3. Now the DNA polymerase 3, it doesn't bind direct to this strand. It doesn't. It will look for somewhere to start on. Now, who is going to provide that starting point of the DNA polymerase 3? That is known as the RNA primerase. This enzyme that you are seeing here is known as the RNA primer. It is going to form RNA nucleotide base, which is going to act as the binding site of the DNA polymerase 3. So when this thing is not there, this base, the RNA base is not there, then boom, danger. The DNA polymerase 3 is not going to have any function because it's not going to bind to the DNA. So as we are seeing, we can see now that okay, the DNA now can come in. It will come in. Boom. This is now the DNA polymerase 3. So this side, the RNA forms the primer, then the DNA polymerase 3 binds. It will be forming. This side, it will be forming like this. Then this guy will now start building. It will be building, boom, 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 boom. It will put the DNA nucleotide bases here, pop up, building the leading strand. So this is what we're saying. This guy will build the leading strand. Let there be the leading strand. So the leading strand is actually continuous. It's just going to be following the replication fork. Now, this guy, that's where now things get confusing. This guy, it has formed the primer. Not so. But the replication fork, when the DNA polymerase comes in, it will start building the nucleotide bases for the lagging strand. Now, this side, the replication fork is still moving. So again, this primer again will do its job. Again, it binds. So at the end of the day, you're going to have the strand which is like this. You have the DNA nucleotide bases, nitrogenous bases, and this is the RNA. We don't want the RNA, nitrogenous bases, we just want the DNA. So it will be a mixture. It's not going to be continuous. It will be a mixture of the RNA primase, or the RNA nitrogenous bases, and the DNA nitrogenous bases. Now, these RNA nitrogenous bases, even for this one, they are not required. So they're supposed to be removed and again replaced by the DNA nitrogenous bases. That's when now, boom, boom, an enzyme will come in to remove this one, and all the nitrogenous bases for the RNA, because we want to form the DNA, not the RNA. Now that enzyme is actually known as it's known as DNA polymerase 1. The DNA polymerase 1 is the one which will come in now, remove any RNA nitrogenous bases, and put a complementary DNA nitrogenous base. Now, so this guy will be removed, even this one will be removed, even this one will be removed. So this is the one which is removing. We're saying polymerase 1 is the one which is doing that work. Now, after it removes, what do you think about the lagging strand? It's going to be somehow like broken, will be like this. You have the DNA nitrogenous bases, you have the space where the RNA was, then again you have spaces, That's why it is known as the Okazaki strand, because it is not continuous, it is discontinuous. Okay, now after it removes, it start putting back the complementary DNA. So if here you have adenine, it will put thymine. If you have guanine here, what do you think it will put? If you have guanine here, what do you think it's going to put here? It will be cytosine. Okay, so it will follow like that. So after it does that work, like we can see, it's going to be somehow discontinuous. Then this guy known as the ligase will come in. This enzyme is known as the ligase will come in, and it will start joining the gaps. So it will be joining the gaps. You may think of these gaps joins even this one, it comes here, joins the gaps, and there forms the lagging strand. And finally, the lagging strand is going to be continuous. So you've seen how the enzymes work. Very nice. Remember, we started with the initiator protein. Then from the initiator protein, when it's opening, the helicase comes in. The helicase is going to do what? It's going to break the hydrogen bonds. As the hydrogen bonds are breaking, the helicase is moving toward the replication fork. There's going to be an enzyme which is known as the topoisomerase, which will be sealing and which will be cutting and sealing. It will be preventing the stressing of the DNA. Then again, there's going to be this protein which don't want you to get back with your X, so it will be holding it back like you ain't going back to form the hydrogen bonds, my dear, which is known as the SSB protein. Then we also talked about the enzyme which will come in, known as the DNA polymerase 3. We said it doesn't directly bind to the DNA, it needs a binding site which is going to be provided by the RNA primase. The RNA primase forms RNA nitrogenous base which act as the binding site of the what? The DNA polymerase 3. Then it will be making the new strands. On the parental strands, the one which are acting as the foundation strand of the what? Of the new strands. The leading strand forms toward the replication fork, and the lagging strands forms away from the replication fork. And again, it's worth mentioning that when talking about the DNA polymerase 3, it will actually be reading the parental strand from 3 to 5, but the synthesis or the production of the new strand is from 5 to 3. Even on the lagging strand, on the leading strand, it's just the same, from 5 to what? 3. Now when all this is done, there's going to be correction. proof. Is there a mistake which has been made? So both the DNA polymerase 3 and polymerase 1, they're going to act as exonucleases, but the DNA polymerase 3, it is the one which is going to read the DNA and removes any mismatch the nitrogenous bases. It's going to remove any mismatched nitrogenous bases and replace it with a complementary DNA nitrogenous bases. The one which does that is the DNA polymerase 3. So suppose you have maybe this one, we said this is P1, polymerase 1. Does it work? Then the DNA is made. And this is the DNA which has been made. Then these are the new strands. And then this is the parental strand. Then after seeing that this one is not where it's supposed to be, you have guanine here, but here you have adenine instead of having cytosine. This is not the way it's supposed to be. So the DNA polymerase 3 will come, remove either the adenine or the guanine, and replaced by a complementary DNA nitrogenous bases. Okay, so that's how it is. Thank you for watching. Hope you have enjoyed. If you have enjoyed, like, comment, promote our page.